So for the example for subtraction for hexadecimal, everything goes the same way as what we do for binary, only that you have to keep in mind that every carry bit now becomes 16 instead. Alright, so let's have a look at this. For example, this is F minus D. Alright, F is 15, D is actually 13, right? So 15 minus 13, no issue. You get 2 over here. Alright, but what happens when you have 1 minus 7? It's not enough, which means we will have to do a borrow from this 9 over here, isn't it? So this 9 here actually becomes 8 already. Alright, but when you take 1 into here, it literally means that since it's hexadecimal, right? Since we have taken a 16, alright? 16 plus 1 over here becomes 17. So 17 minus 7, you get 10, correct? So 10 in its hexadecimal form is actually A, alright? So now that this 9 here, because it's always a good thing to make it a habit to do the crossing and what number it represents later and all that, so that you don't get confused with doing the change here and there. Alright, so this 8, right? 8 minus 3, pretty simple, get 3. Alright, A minus F. Alright, you know that for A, this is actually 10, this is actually 15, so it's not enough, which means you have to borrow over here again, which means this becomes 7, and then you have 16 plus A, which is 10, right? So 16 plus 10, you get 26. 26 minus 15, right? You get 11. That's where 11 is represented as B for hexadecimal here. Alright, so lastly 7 minus 6, 1. Alright, as you can see that everything is the same as how would you do for subtraction for any other number, but always just keep in mind to write down the base at the end as the answer, and always remember that every carry bit is going to represent the base number that it represents. Alright, so if it's 1 here for a hexadecimal, it actually carries 16. Alright, if it's octal, then it carries 8, and so on. If it's binary, then it carries 2. Okay, so I think you're pretty much familiar with this by now. Alright, and then just lastly, I want to just go through very quickly over here. We have something called the BCD. Alright, BCD is just basically a digit of decimal number coded being using binary, and usually it goes by 4-bit. Alright, so BCD is just very simple. 987 in decimal literally becomes, for its BCD, its equivalent. How it works is that it's always being converted into 4-bit equivalent. Alright, very, very simple. What do we use it in? Digital machines, clocks, digital calculator, voltmeters, and so on. Okay, addition, same way, so I would not want to, oh sorry, I think I have, why would I actually have pressed it all the way too far? So yeah, this is where we are. I'm not so sure if you have seen this before, but you know, like sometimes when you see a digital display where things can change and all that, so that's part of concept of BCD to 7 segment decoder. That's what they call it. Alright, where you can change the display and you can light up the parts that you want it to light up at. Alright, according to 0, 1, 2, 3, 4 all the way to 9. Alright, that's I remember doing this as one of the experiment last time, but I don't think you will be exposed to this in this course, but just good for you to know that what it actually is and so on. Alright, this is just a representation of decimal, binary, hexadecimal. Alright, as you can see, these all zeros and ones. Alright, for hexadecimal, this is A. Alright, for BCD, do you notice the difference here? It all just goes, it's kind of the same as binary, only that it's being represented as 4. It's a multiple of 4 bits. Alright, that's just how it goes. We have another thing called the ASCII conversion and stuff, just for you to know that we do have such thing for its conversion. just a table of what we have over here. Okay, besides that, you can see that we have Unicode, we have ASCII characters, and so on. How they actually use to do the conversion and all that. They have each way, or each system, each code has their own way, but we were not going to look into this all, more to just general knowledge for you, and just how it could look like, all right, over here and stuff. Just an application of how tablet counting control system is, and so on. All right, so here we have reached the end of lecture 2. So if you just look at it, the most important thing is for you to really know or differentiate between digital and analog, and then the conversion, very important, from binary to decimal, or decimal to binary. So once, and binary numbers or even decimal numbers, what do you do when it's integer, and what do you do when you have a point form to it? All right, so very important of how you know how to do it. Once you're familiar with the binary form, for you to do the hexadecimal form or octal form, method is the same, only that the number is different. When it involves addition or subtraction, same way, only that you always have to remember each carry bit represents the base number itself. Alright, so if it's a base 16, your carry bit of 1 actually carries 16. Alright, actually carries that much of a number or a value. Okay, so hopefully you have understood this pretty well, and thank you for your attention. Any parts that you don't understand and all, we can always meet up again in our next class, and we can discuss more about it. All right, so happy trying out. Do give yourself some practice over whatever that you have seen. Okay, thank you.